Hello. In this video we want to talk about the dot product and how it relates to the correlation coefficient. So let's get started. Just definition. A dot B, these are vectors. We could have said A inner product B, these are the same, different notation for the same thing. And by definition, this is the sum of AI, BI, from I equals 1 to n in Rn. Okay, so let's go into R2 and see some examples. We've got a vector A here and a vector B here. And I'm going to call A, let's call it 1, 2. And we could say that B is equal to, 2, 0. A dot B by our formula here is just going to be equal to 2 times 1 plus 2 times 0, which is equal to 2. Okay, what if we'd had something like this? We'll let B be the same vector, but now we want A to be shooting off this way. So we can say that A is, we're just making this up. A could be equal to, say, -3, 4. B is the same thing, so we get that A dot B is going to be -6 plus 0, which equals -6. Okay, so these are some examples, and we're getting some idea about what's going on. It seems that if A is in this quadrant, you'll get a positive dot product. If A was in this quadrant, you'd get negative. What if A and B were aligned with the coordinate axes themselves in our xy plane? So let's just have A equal 0, 1, B equals 1, 0, and A dot B is equal to 0. Okay, so something happens here as we approach the y-axis. We're going to approach 0, and then we can grow from there in the negative direction. So we've got some sense of what's going on here. Okay, I'm hoping that this example is very informative. We're going to let B be a unit vector in the x direction. And we're going to let A be this guy. Let's call it 4, 3. So, if we take A dot B, we get 4. Now, what I want you to see is that if we let our head of A just drop to the x-axis, we might ask how far along the x-axis A has traveled. And what we end up with, and the name for this is called the projection. So the projection of A onto B is equal to this scalar quantity 4. Now, in fact, B may not have been a unit vector, but we could have very easily made it a unit vector by dividing by its own magnitude. So we could say something like the projection of A onto B in general, and B also didn't have to be on the coordinate axis for this to hold. The projection of A onto B is just A dot B over the magnitude of B. Okay, so so in this way, we can see that a dot product relates to sort of how far one vector has moved in the direction of the other, provided that you've made the vector you're projecting onto a unit vector. Okay, let's take it one step further, and let's pretend that A had been a unit vector also, which we could simply have done by getting magnitude of A down here in the denominator. So let's start with something like this. Okay, so let's draw two unit vectors. This is a unit vector, and this is a unit vector in this direction. Now what we want to see here is that we can get at the angle between these vectors using simple trigonometry by doing this projection. Because if this thing has a length of 1 and this thing has a length of 1, then we know that the projection of A onto B is equal to, well, it's equal to this x value right here. And we know from trigonometry that the cosine of theta is that x value. So, if we were on a unit circle, this point would have coordinates cosine theta, sine theta. And we're concerned with the x direction here. So we know that if A and B are unit vectors, the projection of A onto B is equal to the cosine of theta. And we can say that for any two vectors, whether they're unit or not, they can be made unit in this way. So we can say in general, the cosine of the angle between any two vectors is their projection onto each other. Were they unit vectors? Okay, and so this is our important relation here. Okay, so we're going to just take the results that we just came up with, which is that cosine of the angle between two vectors is equal to their dot product over the product of their magnitudes. And I'm hoping I was able to convince you of that. Now, we want to bear in mind that this definition, this way of thinking about the angle between two vectors applies not just to R2, not just to R3, but to Rn. So we can now talk about the angle between vectors in any number of dimensions. Sorry, and I should just go through and show that we can then take the inverse cosine of this piece is just going to be equal to the angle itself. So that's a very sloppy theta. Okay, so you might be asking, well, what on earth does this have to do with correlation? Sample correlation. Well, let's recall the formula for sample correlation. R is equal to 1 over n minus 1 times the sum of xi minus x bar over the sample standard deviation of x times yi minus y bar over the sample standard deviation of y. Oh, sorry. I guess I should go ahead and make those sample, not population. Okay, so this is our formula for the correlation coefficient, and a lot of the time you get this sort of thing thrown at you, and it's like, okay, well, where does this thing come from? Okay, well, consider your data vector x. Like, let's say you had 10 points in your data vector. Oh, and sorry, just to contextualize further, this is like each I represents an individual, and this is two measures on each individual. So this could be like x could represent height, and y could represent weight. So you take 10 people, and for each one you record a height and a weight. And R is supposed to be sort of quantifying the extent of the relationship between these two variables. What does knowing the value of height tell you about the value of weight? Does an above average height suggest that you'd have an above average or a below average weight? Well, of course, an above average weight, and this is why there's a linear associationship between, a positive linear associationship between those variables. Okay, so let's move on. What am I on about here? You've got your data, 10 data points, whatever they are for height, and from each one of those you're going to subtract the mean. So what you could consider this a centered xi minus x bar is a centered data vector, which is good because now each point, instead of representing some arbitrary some arbitrary value, it tells you how the value of that data point relates to the mean of the data that you've sampled. Okay, so this is a new vector, and we're just going to call it, for simplicity, A. And likewise, yi minus y bar we're going to call B. Again, these are just new vectors that contain the same information as our data, but they tell you about how the values relate to the mean of the data. Okay, so we can start to rewrite this a bit. First of all, these sample standard deviations are constants, so they can come out of the summation. So I want to write something like 1 over n minus 1 sx x sy times the sum of ai bi. Okay, well, the sum of ai bi we've already defined to just be a dot b. So now we have something like r is equal to a dot b over n minus 1, and what I'm going to do is unpack these definitions of sx and sy. So we get 1 over n minus 1 times the sum of xi minus x bar squared 1 over n minus 1 sum of yi minus y bar squared. And since these are, that would be for sample variance, but we need to be taking the square root of these. Okay, very well. Now, we know that what we have right here is just the sum of ai, because it's squared. Okay, well, what do we know about a dot a? We know that that's equal to the magnitude of a squared. I'll show that in another video. So basically what we get here is that r is equal to a dot b divided by n minus 1 square root of the magnitude of a squared over n minus 1 square root of magnitude of b squared over n minus 1. Alrighty. Well, clearly these guys want to pop out of the square root. So this is just the denominator here. We get n minus 1 times the magnitude of A, magnitude of B, over the square root of n minus 1 times the square root of n minus 1. Okay, well, square root of n minus 1 times square root of n minus 1 is just n minus 1. The n minus 1s cancel, and we're left with r being equal to A dot B over the magnitude of A times the magnitude of B. So what we've seen here is really nice. This n minus 1 in the definition of the sample correlation coefficient, its only real purpose is to cancel out the n minus 1s, the two square root of n minus 1s that are going to pop out of the definition of sample variance. So why it's there is really no mystery. It needs to be to cancel this guy. And what we see is that the definition of R is precisely what we started with as the cosine of the angle between the vectors. So in this way we can see what the intuition is, that if vector A and vector B are highly positively correlated, the angle between them is going to be very small. Like suppose in R2 we had something like this. If this was A and this was B, we can see that the more related A and B are, the smaller theta is, the closer that cosine theta should go to 1 as A becomes more like B, or as B becomes more like A. And as we know, if two things are perfectly positively correlated, R is equal to 1. Suppose R was equal to 0. Well, what that means is that the cosine of theta goes to 0. And this happens as A and B become as unrelated as possible. Okay, so I'm gonna stop there, but hopefully this gives you the gist that the correlation coefficient is really just talking about the cosine of the angle between the two vectors. Imagine if you had 100 data points, you're actually quantifying the angle between two vectors in R100. So you can see that it would be very difficult to visualize this type of thing, but we've hopefully just built the intuition that this corresponds to what you would see as a linear relationship if you plotted out all of your x and y's. All right, thank you.